Okay, hello everyone, it's Salar and we are in part 33 of our tutorial, a tutorial to writing a real-time operating system. In previous part, I've started to talk about interrupt and exception. And in this part, I wanted to continue to talking about interrupt and exception, but in this time about interrupt and stack, because stack is so important when you want to have interrupt and exception in your processor. Okay, but before according to previous part, when you are in your program flow and you jump to an interrupt, you have an interrupt handler. This interrupt handler is a common function, is a simple function. Okay, and after that, returning from interrupt handler your this function to the program flow. But interrupt handler is like a function, simple function. But how you can use a simple function as an interrupt handler? Okay, in this part and next part, I want to answer to this question. But before to talking about interrupt, let's have a review on function call and stack. Assume I have an example here. In my main function, I have a local variable, I have variable plus plus, jump to Solar function, and after returning from Solar function, another time variable plus plus. If you see the compiled code of this program, you have your main function and you have your Solar function. In the first instructions, in main function, you have some instructions to do stacking and create a stack frame for this function. After that, you have first variable plus plus, jumping to Solar function, another time, next variable plus plus, variable plus plus, jump to Solar variable plus plus. Here is main function and here is Solar function. Okay, but pay your attention first on register R7. As I said in previous parts, you have the stack frame and address in register R7. Okay, when you want to jump to Solar function, you need to change the value of register R7. But in next instructions after jumping to this function, you need to register R7 after that. Okay, but in Solar function, your program puts the value of register R7 in the stack, and before returning from this function to this line, pop this value to register another time. So in this instruction, you have the initial value of register R7 and you have no problem. Okay, but now pay your attention to register R3 in this time. Okay, let's inspect that. As you can see here, here is variable plus plus. First, read the value of variable from stack to register R3, variable plus plus, register R3 plus 1, and after that, store the value of register R3 another time in the stack memory. Okay, in the local variable. So in this line, you don't need the value of register R3 anymore. So when you jump to this function, there is no problem. You change the value of register R3 in this instruction, but there is no problem because in this line you don't need the value of register R3 anymore. Okay, and after returning from this function, your program load a new value to register R3. Okay, you don't need the initial value. So let's give you some information about ARM standard. According ARM architecture procedural call standard, for register R0 to R3, register R0, R1, R2, and R3, these registers called temporary registers. Why and what is temporary registers? The compiler must guarantee when a program wants to jump to a function, for example here jump to Solr, okay, the program doesn't need the value of these registers R0 and R3 anymore. So before to jumping to this register, the compiler guarantee you doesn't need the value of register R3, for example, anymore. So in this function, you don't need to push the value of register R3 to the stack, okay, because of ARM standard. And GCC compiler guarantees this standard, and it's related to implementation of a compiler and code generation in compiler, and it's out of our topic, okay, but the compiler must guarantee, and according to this guarantee, GCC guarantees this standard. But let's to see another example. For example, assume that you have your main function, another time Solr function. In Solr function, you have an array and you want to return the summation of these contents, okay, you want to return this content. And in your main function, you have Solr, return value of Solr plus Solr, and put the summation in this local variable, okay. So in assembly program, we have jumping to Solr function couple of times, 1 and 2, okay, couple of times. You need to jump to the Solr function couple of times, 1 and 2. But in this time, pay your attention to register R4. Assume that in this line you want to jump to the Solr function, but before that, before returning from this function, as I said in previous parts, you have the return value in register R0, and your program has returned this value to register R4, and after returning from this function, you need the value of register R4 in this instruction, okay. So you need to preserve the value of this register in this function. As you can see in this function, the program has pushed the value of R4 in a stack because you want to change the value of register R4 in this line, okay. So push the value to the register before returning from this function to this instruction, pop register R4. So in this instruction, you have the initial value of register R4, and after that, another time in this instruction, you have the initial value, this value. So you have no problem because of this preserving, pushing the value of register in register, pushing the value of register R4 in the stack by this instruction at the first instruction in this function. But another time according to procedure call standard, but in this time for register R4 to R11 are known variable registers according to a standard, but in this time compiler doesn't have to guarantee, okay, the compiler doesn't have to guarantee that in this line we don't need the value of register R4, okay. For register R0 to R3 in this line, before jumping to a function, your compiler must guarantee that the program doesn't need the value of register R0 to R3, but for register R4 to R11 it's not necessary. As you can see, you have the value for register R4 here, and you need this value here, okay. So when you want to use these registers R4 to R11 in your procedure, you must or compiler must push them, register R4 to R11, to the stack, because the color function may have used them. You want to change the value of register R4. You want to change, for example, the value of register R7. For example, R4 or R7. You need to push this value in register because the color function may have used them. As you can see, the color function used register R4 and R7 another time after jumping to this function and return from that. You don't want to, for example, use register R5 in this program, but your procedure must push this value because you want to change that. Okay, you don't need, but the procedure must put this register in a stack. Okay, for register R4 to R11, it's a standard. If you want to use this register in your procedure, you must push the value of these registers in a stack. Okay, but it's not necessary for register R0 to R3. But now let's talk about interrupt and register values and stack in the interrupt. Another time, I want to inspect the first example in this part. In previous example, I had a solar function jumping to a solar function here, but here I don't have. Okay, here I don't have, but here I have an interrupt handler. Okay, I have a system, for example, systematic handler. Let's to see the assembly code. Another time in this line. Okay, I said in this line you don't need the value of register R3 anymore in this line, but assume that you have a jumping to an interrupt suddenly in this line. After this instruction you have a value in register R3 and here you have an interrupt. Okay, suddenly you have an interrupt. You want to change the value of register R3, but your program doesn't push the value of register R3 in the stack. So in this line, if you jump to the interrupt handler and after that return to this instruction, you need the register R3 another time. But in the systematic handler, the program changed the value of register R3. Do we have a problem here? No, we don't have a problem here, because in ARM processor, hardware solves this problem. Let's see this slide. For interrupt, just for interrupt, not function call, just jumping to interrupt and exception. Before jumping to interrupt handler, for example here, before to jumping to interrupt handler and start to running this handler, the processor, hardware, not compiler, puts some register in a stack. These registers. Here is a lower address and here is upper address in a stack. Your processor puts the value of these registers in a stack. And before returning from interrupt handler, pop these values to the registers, to their registers. Okay, register R0, R1, R2, R3, register R12, link register, return address. For example, here is a return address, here is return address, program status register, and a padding. What's this padding? According to this formula, if the stack pointer, before to jumping to interrupt, if a stack pointer modulated by 8 is 0, you have no padding. But if stack pointer modulated by 8 is 4, you have a padding here. Why? Because when you want to jump to a function, you need to have the stack pointer as a double word aligned value, okay, and it guarantees that. Okay, for example, in Cortex M7 you can disable this facility by writing some value in system, in system control block and I think TCR register. Okay, you can disable this facility, but if you want to have no problem, you have to enable this facility. And for example, in Cortex M7 I think you can't disable this facility, but for example in Cortex M4 and M3 you can turn on or turn off this option in your processor. But in Cortex M7 it's a default option, okay, and you can disable that to have a padding. But let's do back to our problem. I said before to jumping to an interrupt handler, your processor puts the value of register R, for example 0 to R3 and some other registers in a stack. So if you jump to system handler and return that, you have the initial value of register R3, and it has been guaranteed by processor, not compiler. Okay, but let's see another example. For example, in this time or second example here. Okay, this example for okay. But assume that in this time you have a interrupt handler, and for example in this line you want to jump to systematic handler. As I said, in register R0, after returning from this function in register R0 you have the return value, but you want to jump to the systematic handler. You want to change the value of register R0 in these instructions, but because the processor puts the value of these registers in a stack after returning from interrupt handler, you have the initial value of register R4. Okay, so you have no problem, and you can easily for example use a simple function as an interrupt handler. Okay, a simple function, you can easily use a simple function as an interrupt handler. So to support interrupt by the compiler, it's not necessary to push the value of register R0 to R3 to the stack, because the hardware does that, and the hardware has done that. Okay, but it's necessary to push the value of register R4 to R11 to the stack by compiler, and according to ARM architecture procedure called standard, the compiler guarantee this. Okay, guarantee preserving the value of this register. Okay, so you can easily use a function as an interrupt handler. Okay, I will continue this topic in next part, and I give you some information about function and interrupt handlers. Okay, especially interrupt, intry, and return from exception and interrupts. Okay, in next part I will give you some information about returning from exception and interrupts in ARM architecture. Okay, thank you very much to see me, and see you soon in the next part. Thank you very much.